Greetings from Washington State University, Pullman campus. For the past couple of months, our team, comprised of WSU Robotics Club members and mechanical engineering students in their capstone course, have been working towards designing and constructing a fully functional rover to compete in the University Rover Challenge this coming June. In approaching this task, we split our team up into 3 subgroups: movement and frame, claw and science capabilities, and programming. The movement and frame team was tasked with ensuring that the rover's locomotion, suspension, and chassis are designed and constructed in a fashion that will not only meet, but also exceed the URC guidelines and requirements. To achieve this goal, some of the design choices made included selecting Bosch tubing and acrylic for the frame due to their low weight and high strength, as well as a rocker bogie suspension system due to its simplicity and wide range of motion. In addition, these design decisions were preferable since both Bosch tubing for the frame and aluminum for the suspension are readily available on campus. The claw and science capability team was tasked with designing the arm, claw, sensor array, and sample storage containers. The structure of the arm is composed of its base, multiple arm segments, each consisting of adjacent aluminum sheets attached in between each other, 2 DC motors for full rotation at both the wrist and base, and 3 linear actuators in between for a full 5 degrees of movement. For the claw, we decided to move forward with a 4-jaw design. We anticipate that such a design will provide better gripping power and contact than that of a 2 or 3-jaw design. On our sensor array, we have 2 probes. The 3-prong probe can measure the soil's relative humidity, electrical conductivity, and temperature down to 5 centimeters. Since the competition calls for a reading 10 centimeters below the surface, we made sure to include the side-mounted 15 centimeter temperature probe as well. To collect the sample, we plan to utilize a simple boring bit that will be both depressed and rotated into the soil, and then will be ejected through the use of an attached linear actuator.
We are designing an integrated system consisting of an Intel NUC centered around a network of Arduino microcontrollers that will run all of the peripheral equipment associated with the rover. An array of cameras situated on the front of the rover body, as well as lofted above on a boom, will assist in object detection and avoidance during the autonomous portion, and then provide multiple points of view during the driver-assisted missions. The NUC is meant to be the central computer of this system, handling all sensor input from each of the surrounding Arduinos and sending instructions back out to each of them in turn. One of the Arduinos is dedicated to positioning and movement sensor input, outfitted with a GPS breakout board and LiDAR for accurate location data and advanced obstacle detection, while the rest of them are dedicated to the control and monitoring of the various motors situated around the rover through Sabertooth motor controllers.
So we have already designed our rover for an internet-based remote control and video streaming, and that system is tested and functioning. We have done preliminary testing of a second remote control system using 2.4 gigahertz radio control, and we'll implement the better of the 2 systems in the final design. We are using OpenCV and Python and have developed an object detection algorithm to help us complete the autonomous portion and to assist the pilot to identify key items to complete the competition.